based earthquake, disasters. So we're looking at earthquakes, tsunami, and volcanoes, all as a result of plate tectonics. And what we looked at when we were looking at the things that came about after Alfred Wegener's failed theory, one of the things, again, were the distribution of earthquakes and volcanoes. So now I'm showing you a modified version of the slide you saw before, where you can see the location of earthquakes. And we note that for the most part, though not always, the big earthquakes are restricted to the plate boundaries. You now know about how plate boundaries work and what's going on. One thing that I'll show you as a sort of warm-up to some terminology is there are 3 different colors here. And you can see the red are shallow focus earthquakes, the green are intermediate, and the blue are deep, which is really kind of cool because what you're looking at now is the depth that the subduction zone plate, the one that's being subducted, is located. So you can see when we're talking about Japan, for example, you have 2 plates, one's coming down, diving down under the other one, and the earthquakes that are close to that boundary are shallow. The ones that are a little farther away from the boundary are intermediate, and the ones that are so deep that they're the last thing that happens before that plate actually melts are the blue ones that are far, far away. Those tend to be the big ones because they're under a lot of pressure. So you see over on our continent and our plate, most of the big earthquakes are shallow focus, and they are actually, because you have a transform boundary there, and there are actually no deep focus earthquakes there. So deep focus earthquakes tell you that's a subduction zone. Plate is diving down. So we know that earthquakes are not randomly distributed around Earth. We will also find out that there are earthquakes that are away from plate boundaries for different reasons. But when we're looking at this map, it's a little bit maybe confusing at first because earthquakes don't happen at the surface. You wouldn't have a crack appearing at the surface. Earthquakes happen deep down in the Earth. So we've got to start looking at terminology and seeing what is an epicenter versus a focus versus the fault. First of all, what are earthquakes? You can define earthquakes in many different ways. It is the elastic failure of rocks. So the failure of rocks in an elastic fashion is an earthquake. What you can see here is that these rocks are bending, right, in picture A. All rocks, when you expose them to this differential stress, are able to bend. And the amount of bending that they can have before they break is related to their material properties. Also related to a couple other things that aren't on this slide, such as the time over which these are important even though they're not on here, the time over which you apply the force. And maybe you don't have a good feel for this with rocks, but think about a pencil. You can take a pencil and apply force instantly and get it to break. Or we could have a pencil in, I don't know, a vise here, and every day that we come in, we give the vise a little bit of a turn. And over the whole course of a semester or the year, if you apply that same force over a long time, you can actually get the pencil to bend into a U shape. So the longer the time over which this force is applied, the more likely rocks are to bend rather than break. If you have a quick, instantaneous force that's happening, then it will break. Also, the confining pressure. There are experiments that have been done in the lab with looking at taking a column of rock, of different rocks, and exposing them to pressure. So you're squeezing them in this way. And if you don't have any confining pressure, the rocks will shatter. But if you put a jacket on them and expose them to confining pressure and apply that same force over the same amount of time even, you can get the rock to bend if you're really supporting it on its sides. So the rocks that are deeper down in Earth have a lot of confining pressure, so those would tend to bend rather than break, where rocks up closer to the surface that don't have a lot of confining pressure, the environment favors breaking. And so then also temperature. We talked about volcanoes and the temperature at which magma crystallizes out of a melt. If you have a low temperature, you're going to favor breaking. And by breaking, I'm saying earthquake. If you have a high temperature, right, so those rocks are diving down the geothermal gradient, it's getting warmer and warmer in the subsurface of Earth. When you have really warm temperatures, that will also favor bending rather than breaking. So you have to take those 3 things together, time, confining pressure, and temperature. And that will tell you, based on the specific rock that's present, is this rock going to bend? Remember we looked at metamorphic rocks with all those bends in them. Or is it going to break and have an earthquake? So elastic failure of rocks. You can also define it as a rapid slip along a fault. So you see here, earthquake has happened, snapped. And the thing that emanates from this are seismic waves, which are similar to sound waves. So we'll look at the seismic waves later. But let's return to this whole notion of what's plotted on that previous map, those circles. We know the earthquakes are deep down within Earth, so how do we plot them on a two-dimensional map? There are three fundamental pieces of terminology that you should understand when looking at earthquakes. They're the sound waves, the seismic waves that are emanating out from the focus. So first we'll talk about it, even though it's not in this order, the focus. The focus is the point from which the rupture emanates. It's the point at which the energy is released. So the focus is the physical position inside the Earth. So that's where the break starts from. What we plot on a map is straight up, vertically up from the focus on the surface of Earth. That's the epicenter, so that enables us to plot earthquakes on a two-dimensional map, right? And the third part here is the fault. That's the whole physical expression of the damage. So if you're at the land surface, you're talking about the fault right here. You know, that's the crack that extends down into Earth. So you can imagine that if you play with the angle of this fault, then you can get the epicenter and the fault to be coincident, right? If this were a vertical break, which sometimes happens, right? Then when you break the rocks, one slides past the other, then the epicenter and the focus are the same. But if you take that angle and you make it even more shallow, it's called a thrust fault. So you start over here, you have a very shallowly dipping fault. Then the fault, the broken up rocks, can be miles away from the epicenter. So if you have this very, very shallowly sloping fault, the broken up stuff's here, the epicenter's here, and the focus is down at that point of rupture. So those are the three different things that we plot on a map. And the epicenter, again, is a surface expression directly above the actual earthquake. The focus is the physical position inside Earth. The fault is the broken rocks. So remember that I try in this class to tell you that there are good things about these disasters too. They're not all murder and mayhem, right? With volcanoes, they make wonderful soils for great agriculture. And they make wonderful soils for wineries as well, talking about all the wineries over in Europe. Lots of volcanic material. There are bad things, though. Destruction, you see here, tremendous damage as a result of earthquakes. It's no coincidence that the countries that spend the most amount of money on earthquake research, China, Japan, the United States, Russia, are also the countries that experience the most death and damage as a result of earthquakes. So we are interested in them because we want to try to mitigate, remember this word from the first day of classes, the damage. How can we lower the death toll from these things? How can we engineer buildings? How can we implement land use planning such that we are minimizing on this catastrophe that happened? And we'll talk about the predictability of them. But these are one of the worst disasters because we don't know how to predict them. We spend billions of dollars trying to figure out how can we predict earthquakes. And they remain pretty much the most unpredictable of the disasters. So the death toll gets to be quite high. The good thing, a good thing though, is that the second day of classes, we talked about from a course point of view, the layers of Earth, right? The layered structure. We know what goes on inside Earth. We know that the core is a solid metal ball. We know that the mantle is this glassy, siliceous stuff that's viscous, that's almost solid but still capable of flowing. Again, this is from a very general point of view. And the crust is solid. How do we know that? Do we have some sort of Jules Verne machine where we drive down into the center of the Earth taking chemistry and temperature measurements? No. We got all of our information about inside of Earth from earthquakes. So this is a picture. You can't read the text here, I'm sure, but it doesn't really matter. What I put it up as a graphic to show you is that as we trace teleseisms, earthquakes that are so large they can be felt with seismometers all around Earth, there's the earthquake focus at 0 degrees. Not necessarily saying that an earthquake is going to happen right at the North Pole, but that's where the location of the earthquake is. Seismometers placed all around Earth found some really interesting things. From 0 degrees to 103 degrees, the waves that we're going to talk about in a minute that emanate out from the point of rupture are detected exactly as we'd expect them to be detected. There's 3 different waves. So you see these waves coming, you see them in a very predictable fashion. From 103 to 143 degrees, there's something called the shadow zone. And we'll see, sorry, that one inside, we'll see in a minute that there's one of the 3 types of waves that does not pass through liquid. And so it is this disappearance of the wave that does not pass through liquid that gave us proof positive that there is a almost solid but still liquid portion of the interior of Earth. And that is the whole point to plate tectonics. That's how plate tectonics can happen, because there's liquid. We know there's liquid because of this shadow zone. And then from 143 to 143 on the other side, again, just relative to 0 degrees being the rupture, the waves are all found, but they're jumbled up. They're mixed up. They have been reflected. They have been refracted. Things have gone on to them that make the stuff from 143 this side to 143 this side nonsense. It's not what you'd expect. And it took geologists a while to kind of unravel how this is the way that it is. So they gave us valuable information: core, mantle, crust, lithosphere, asthenosphere, mesosphere. We found that out by looking at earthquake waves. Just like they gave us information about the deep Earth, they're also very valuable at giving us information about the shallow subsurface. So seismology, shallow subsurface, we're talking about the stuff right up in the crust where we are. So for example, I'm a groundwater geochemist, and when I need to get something that I need to look at, I have to drill a well, or have someone come drill a well for me. So drill a well down into the earth, down to the point at which I need it, and so I can take my groundwater samples and see what's in there and how deep the water is and all sorts of stable isotopes and whatever it is I need. But I also want to know what's in the subsurface in my whole study area. Sometimes it's small. You're doing a job site down in Boston and you have, a quarter of an acre. You want to know what groundwater's doing there. It's a little easier. Drill 3-4 wells, get a good idea of it. But sometimes it's over, like with my PhD research, it's over, hundreds of square miles. Vast circumboreal peatland in northern Minnesota, going into North Dakota, up into the Hudson Bay lowland. And I need to know what's going on so I can figure out what groundwater's doing. But it costs between $6,000 and $10,000 to drill one well. And you pull up the core, and you can see what's there, but just at that one spot. And so it's not very helpful if I want to know what's going on for 100 square miles. So what we did when we were looking at this peatland is to create earthquakes. Stick dynamite into the ground, detonate dynamite, and then have seismometers some distance away. And the way that the waves, which are artificial earthquakes, but it works the same way, the way that the waves travel through the material gave us absolute information about where the peat is, where the plant material is, when it transfers down into really degraded stuff that's clay, and where the bottom is, where the rocks are. And I could do nothing else about constraining the geochemistry of this wetland without knowing that fundamental information. So this is done all the time. People like me, love earthquakes as long as they don't damage things or kill people, because we can take the way that they pass through the shallow subsurface and very effectively constrain what's going on there. And that enables us to see where should we build, where shouldn't we build. You can also sometimes see if there's an oil reserve. You can see a lot from Earth's surface by the way that these waves travel. So here we have 2 good things and 1 bad thing. A couple more good things with earthquakes. First, hydrothermal vents. We kind of talked about hydrothermal vents a little bit when we talked about divergent boundaries. water, hot water traveling through these earthquake fault boundaries. And as they come up towards the surface, the water progressively cools and deposits or precipitates out the high amount of dissolved solutes that are there. This is a picture of a gold mine in Idaho Springs. The blue-green colored mineral is copper. So what you can see is that there's an earthquake for scale. There's a geologist's hand. There's a valuable seam of copper there that we can actually mine and use. So they are really, really good at forming and then also exposing mineral resources. So we need copper. We need all sorts of things that we can find in earthquake fault boundaries. And then this last part here, they can contribute to energy resources. GW stands for groundwater resources. So this is a petroleum seep in Ojai, California. It's a result of the 1994 Northridge earthquake. There was an oil reserve that was not mapped. We didn't know it was there. An earthquake happened. Fault zone was created, and that oil that was deep within Earth started seeping out. This is all oil. And so then we can go and develop an oil drilling situation and get that natural resource, get that oil. Oil is a fluid. Just as you can do this with oil and gas, you can also do it with groundwater. Yeah.
Where was that located?
It's in Ojai, California, Ojai, and it's after the 1994 Northridge earthquake. You don't need to get into that level of detail, but so they're good at forming and showing where these energy and mineral resources are. They're also bad. The things that happen in earthquakes, I'm putting these out, and I'll go through them a little bit rapid fire, because this is where your book is going to start to be important. You'll start looking at what happens in an earthquake. And this is where, again, you will have 3 different earthquakes that you're going to read about, but you'll see the recurring themes to them. The adage is, I may have said this the first day of class, is earthquakes don't kill people, buildings do. And I told you taking the students to Iceland, and there was a big earthquake in Iceland, and people's parents were calling in saying, oh my gosh, is my kid okay? But they were camping. So I was able to tell the parents, yes, absolutely, your kid is okay. No problem at all. In a way that, again, if they were in a heavily urbanized area, especially with poor building materials, I would not have been able to say your kid is okay. Earthquakes don't kill people. So this is a picture of what happens in buildings. Buildings can sway, and as we'll see, you want them to sway. The more they sway within reason, the less likely they are to pancake. And pancake, you can see, is just the walls giving out, and the ceiling of one floor becomes the floor of that floor. So buildings can sway. Eventually, in extreme cases, they can pancake down onto themselves. Another very, very bad problem associated with earthquakes, you'll see this with the 1906 San Francisco earthquake you'll read about, with the Lisbon disaster that you'll read about, which is actually in the tsunami chapter. It was an earthquake that caused a tsunami, so it's in the tsunami chapter. You have rubble all over a city street. It hampers efforts of rescue relief workers, but also emergency workers like firefighters. And so you have fires and explosions potentially all over the place. Happened in the so-called olden days, like Lisbon, 1755. We didn't have electricity then. There were fires burning. It was All Saints' Day. It's one of my favorite horrible disasters to talk about. So on All Saints' Day, everyone was in a church. And all these Catholic churches all over Lisbon, and they were ornate and beautiful, but very heavy, and they didn't fare well in the earthquake. So the churches all were destroyed by pancaking, but then also they had fires lit in the altars, and so everything burned. So it was really, really awful. So again, this is a fascinating case study you'll read for next week for the tsunami, but it was an earthquake, destroyed Lisbon. People were in the churches. The churches all were destroyed. And then people ran down. Then everything started to catch on fire. People all ran down to the ocean to get away from the fire. It was, the whole city was in flames and in ruins. And that's when the tsunami came and killed the rest of them. So it was awful, awful. And then a dust storm was a quadruple disaster. It was awful. It's interesting to talk about this at a Jesuit school because it was a paradigm shift, this earthquake, sort of as an aside. at first, when this happened, it was one of the most pious cities in all of Europe, and people thought this is the work of a vengeful, angry God who's smiting sinners. There are sinners among us. There was a little faction of atheists there, so they thought God was smiting sinners. But then, when it was such a big disaster that earthquake and tsunami reports are coming from all over Europe and from elsewhere, and this paradigm shift was quite powerful and persists to this day. That these things are not God smiting sinners. They are natural processes as a result of something that's happening in Earth, and we are hapless victims of this, and we have to figure out how to recover and rebuild and make things safer for future generations. So all of the things that we're seeing here happened in the Lisbon disaster, also in the Sumatra tsunami, also in the Fukushima and Tohoku earthquake and tsunami. So, explosion. Back in the day, altars, candles, people using open fires for cooking. Today, we have gas lines crossing the city. And when you rupture them, now you have gas issuing forth, right, in a vaporous phase or in a liquid phase all over the place. You have power lines with electricity that snap, sparking everywhere. So you imagine this is pretty volatile. And so fires oftentimes break out citywide after an earthquake. Liquefaction, you'll see a really, really neat video, I'll send you a link of it, of liquefaction. When you shake unconsolidated sediment, sand, gravel, things that are not rock, and there's water there, what happens is the material will behave like a liquid. And so it would be as if a house was suddenly built on liquid, and it just sinks down. And also deep groundwater can come rushing up, and so you have these water spouts. Really neat footage of the Tohoku earthquake with this liquefaction of sand and clay. So the solid behaves like a liquid. And you imagine, again, if you're building things on this material, those buildings won't fare well. A lot of coastal cities, San Francisco, the Tohoku earthquake, around here, built on coastal sediment, marine sediment that is unconsolidated. So when there's an earthquake, especially in a coastal region, we don't fare very well. And we'll revisit this when we talk about landslides and mass wasting, any slope is, for reasons we'll discuss, stable until you change something about it. And we'll talk about things that will change slopes. But right now, know that if you take a stable slope and you start shaking it, it becomes unstable. So we have these combinations of disasters, right? We looked at volcanoes. Volcanoes cause earthquakes as the magma rises up. Earthquakes can then cause landslides if they're big enough. You shake a mountain, any sort of slope, you're going to have the failure of the material. And then tsunami. So we have all these combinations. If the earthquake happens in a specific way, again, that we'll discuss next week, such that you make a disturbance on the seafloor that perpetuates up to the surface of the water, then you're going to have a wave that is potentially devastating for very, very far inland, depending on the size of it. So again, earthquakes themselves are not terribly damaging. They're disconcerting. So we'll talk about the types of waves that happen as a result of earthquake ruptures. And it's really scary. Again, I'll show you, I'm going to send you a video link to a documentary on the Tohoku earthquake. And this shaking lasted for 5 minutes. And so it's like you're standing on seawater. You have these waves coming through, just like ocean waves with a certain period, and you don't trust the ground beneath your feet. So that's disconcerting, but you can imagine that's not lethal. People actually, in extreme cases, can get seasick because they're standing essentially on water, what's behaving like a water-based liquid. But they're not lethal unless you have all of these things happening. So secondary effects, really. So how big are they? I'm going to put out this, and I'm kind of going to talk about it from the bottom up. There was an evolution in trying to quantify how big an earthquake is. The first scale, so down at the bottom, so I went from most recent to least recent. First scale was developed by a man by the name of Giuseppe Mercalli. And this scale was a scale that measures damage to human structures, kind of the human experience. It was not a scale that quantified anything. It was semi-quantitative. It was a scale that went from 1 to 12, Roman numeral 1 to Roman numeral 12. And I wrote down what Roman numeral 1, not felt by any except a few under especially favorable circumstances. So for example, such a slight earthquake, like the ones we have here, that if you're at rest, you're sleeping in a bed on the top floor of a tall building, you might feel a little bit of a wave. Nobody else would feel it because they're going about their business. And then you go up from 1 all the way to Roman numeral 12, which is damage near total. Ground seems to move in waves. Lines of sight and level distorted. Objects thrown up in air. So it's really interesting. When you have a big earthquake, again, because of these waves, if it passes through a forest, there have been documentation of the wave coming through, and there's trees in the forest, and the trees just get ejected. The roots and everything just get flown out of the ground. So that's 1 to 12. And it measures, again, damage to human structures and the human experience. Can you see why this would potentially fail? Why would this not be enough for us? Think of a couple reasons, yeah.
If there's an earthquake that's not in an urban area or where things are living.
Excellent. You could have a colossal earthquake in Siberia, right? And there was a colossal meteorite impact in Siberia. We didn't even know about it for years later. Exactly. Or the seafloor. 71% of the surface of Earth is covered with ocean, right? Unless it makes a tsunami, you could have a huge earthquake and nobody would feel it. There would be zero damage. Good. Excellent. So it's not helpful except in urban areas. What else? Think of another reason why it might be a little subjective. Think about the damage if you saw this earthquake in Haiti, right? It's a very poor country. There are not good building materials, and so damage was massive. If you had that same magnitude earthquake in, say, Japan or San Francisco, somewhere where we have really good engineered buildings that will withstand earthquakes, it may look like a Mercalli 12 in Haiti, but the same energy released in the same material in Los Angeles would be a 8 or a 4. So it's highly dependent on the building materials. And also has seen that it was a little bit subjective in terms of the person that went to evaluate. So you actually have someone come and look around at the damage and then assign a number. What if you've been a Mercalli appraiser for 20 or 30 years, you're really good at it, you've seen a lot, you've had a lot of experience, it's my first day on the job. It's really, again, it's a subjective thing. So there's no energy assigned to this, and it was a failed scale. We then moved to what people call, which is not, the Richter scale. It's not the Richter scale. The Richter scale was set up for a specific location in California. You should never call anything, any earthquake, something on the Richter scale. We had mostly the same mathematically. There's a correction factor and that makes it universal for all over Earth, and it's called the moment magnitude scale. So the moment magnitude scale is now a scale of energy release. So we measure how much energy was released when that rock broke. And it's a logarithmic scale. What does that mean? Is 7 just a little more? Yeah. Excellent. Excellent. Yeah, absolutely. Thank you. So when you're with a little bit, if you're in a moment magnitude 1 or 2, who cares, right? 10 number ones is a 2, not a big deal. But when you're getting up to these bigger numbers, a 7 versus an 8, a 7 is a substantial earthquake. An 8 is like 10 sevens going off at the exact same time in the exact same place. So that's a colossal increase in energy. And when you get these ones that have been happening recently that are just gargantuan 9s, that's 10 8s at the same time at the same place. So you have this logarithmic scale. It's a huge amount of energy with the bigger earthquakes. So it's, again, log scale, energy release. This right here, magnitude number per year, damage. I used to have a column on this slide that says ergs of energy released, and I took it off because I found that most non-science majors don't have a good feel for how many ergs of energy is impressive versus not impressive. And then people were like, do we have to memorize this? So it wasn't helpful, right? So I took that off. But what I want you to see here is this inverse relationship that we've been talking about with disasters, right? Where the bigger they are, the less frequently they happen. So just to give you a couple of numbers, going from 7.0 to 8.0, This is roughly, globally, how many happen per year. The Earth's been really noisy lately. We've had a lot more earthquakes than normal. And then this is a qualitative assessment in lieu of the ergs of energy release of how much damage you can expect in an average city as a result of this size earthquake. So we move from this, how much damage do we see, to how much energy is released. But that's tough too, because we talked about rocks and minerals, right? We talked about how if you have an earthquake and semi-consolidated, so semi put together but not really put together, like sort of sedimentary rock, it's starting to be lithified but it's not all the way, you're going to have massive damage, but you have the same energy release over here with structurally sound crystalline granite or gneiss or something. You have the same ergs of energy release, and you're going to get virtually no damage here. So now we have kind of the opposite problem, right? We have an absolute value of how much energy is released, but why was there so much damage over there, and with the same exact ergs of energy release over here, there was virtually none? So that's why I put in this modified Mercalli scale. We actually still use this, and it's interesting. The USGS, United States Geological Survey, will send out emails to people who live in earthquake-prone regions after an earthquake and ask about their experience. You know, scale of 1 to 10, how much shaking did you feel? Did any dishes fall off your shelves? And it's really sort of a qualitative survey about what was your experience. And from that, they make shake maps, and they're these sort of roughly sub-parallel areas that show this is where a lot of damage was done, this is where less was done. So you get, going back to kind of Mercalli, how much damage was there? So we use these two things together. Ergs of energy release is helpful, but we're talking about where was the most damage done, where are people most impacted, where do people experience it, then it turns out the modified Mercalli scale is more helpful. So what is it that we're measuring when we are measuring these waves? There are three types of waves. I'm going to go back and forth between this picture and, this slide and a picture. So if you're writing these down, maybe leave a little bit of space. How do we measure seismic waves? Well, let's first talk about what the waves are. There are 3 or 4, depending on how you look at it, types of waves that are released from earthquakes. The first are released. They all get released at the same time. But the ones that travel the fastest are P waves, compressional waves. Compressional waves are very similar to how you can hear me. You could hear me because I am bunching up the air in a pattern, essentially, between my mouth and your ear, or through this amplification device through the speakers. So compressional waves are a situation where the air, or in this case, earth, is expanded and contracted in waves. It would be similar to if I took an eye hook, screwed it into the wall here, had a slinky, pulled the slinky over to here, and didn't go up and down or side to side, but I pushed it like that. What would you see? What would you see? I just went like that with a slinky with all the coils. Some of them would bunch up, right? Others would be expanding, and you'd have this going over and back and forth. So compressional wave, I'll put the next slide up. Here's pre-earthquake. There's the compressional wave. You see the fence, I think those are called stiles, are broken because you have compression and expansion of earth. It's not going up and down or side to side. If you are standing here and an earthquake happened, your legs might come apart and go together a little bit. Not terrible. That's the compressional wave, and those travel the fastest. Again, like a slinky, pushing it like that. Going back up to the previous slide. The next wave is an S wave or a shear wave. And a shear wave is what would happen if I took the slinky down from the eye hook and tied a rope to it. I tied a rope, and I gave the rope a tug like that. What would you see then? What would you see? If I went like this, you'd see a sine wave, right? Going over to the wall and kind of coming back. In reality, it's parallel to the direction of, perpendicular to the direction of motion. So it would be like going back and forth like this with regards to how they travel through Earth. But you wouldn't be able to see it as well if I did this. I'm just tipping it up. So I gave the rope a tug, and you'd see this wave that comes up and down. But again, it's going parallel to the ground. So there's the sine wave. The earthquake, second wave comes through. And now the fence is moving in this undular fashion. If I were standing here through the S wave, I would come forward, I would go back, forward and back. So I'm still not jostling around. So first my legs are going like this, then I'm moving forward and back. And so that is the S wave. The S wave is the wave that cannot travel through a liquid, but it can travel through a fluid. Sorry, cannot travel through a liquid, it can travel through a solid. So this is how we found out that the mantle, the asthenosphere, is liquid-ish. So going back up, the last waves and the waves that are the most damaging are surface waves. They are subdivided. We won't get into this for the purpose of this class, but just in mention, passing. Love waves and Rayleigh waves are both surface waves. Body waves are also called. These are the waves that are defined as the boundary between two media with different physical properties. So they're three-dimensional waves. So the boundary between Earth and the atmosphere. Ocean waves are surface waves. So you watch the ocean wave go through, tsunami waves we can look at as well, through. And so the surface wave is the boundary between the atmosphere and the seawater. You make a surface wave in your bathtub, get in your bathtub and slosh back and forth. And you're making a disturbance in the boundary between two media with different physical properties. So these are the ones that are very damaging. Those are the slowest. So they hit the last. So go down to this picture. Thinking of doing this. Yeah. Okay. So in this case, the fence is moving in three directions. Again, if it were strong enough, those trees could actually come flying out of Earth, and you would have a very bad situation. I have an email that I got from a friend of mine who's in Guam, and she was in a sizable earthquake. And so I wanted to read it to you. It's brief, but it's interesting because she has zero knowledge of science. She's a park ranger, so little knowledge of science. But it really exquisitely narrates this. Hi, friends. Many of you emailed about my status, and I thank you. The earthquake hit at 1 a.m. Saturday morning as I was pulling into a parking space outside a bar. I was going, you didn't need to know that. I pulled into, she was doing something. I pulled into the parking space and was like, oh my God, I hit the car in front of me. Then I realized I hadn't, and my second reaction was, oh my God, I've been hit. So that's the P wave. It's like, she's going back and forth. After realizing that neither of the two happened, I was still shaking violently in my car as the cars in front of me, two big SUVs, danced repeatedly to the left and right. So now you see the S waves going this way. She sees these SUVs moving like this, and she's not in the surface waves yet. The shaking continued, and I saw the pavement become like water as the entire huge parking lot transformed into several waves of moving cement. It was surreal to see the asphalt turn into a procession of moving waves by which my car began to surf, and then all caps. There were traveling waves in the cement. It was quite scary, and me and my car were being moved up and down. So that's, again, the surface waves, when we weren't being shaken to the left and right. So still some S waves are coming. So she's going in sort of all directions. You could see buildings shaking and street lights quit as car alarms screamed. There were cracks in the pavement. Eventually, the shaking stopped. I got out of the car to meet my friend. There were people in the parking lot who had left the bar as things started to shake, fall over. Bottles, glasses, mirrors were smashed. Tables turned upside down. Downtown Truman, where I live, was hit pretty hard as plaster and ceiling parts and a drop ceiling dropped to the floor. People were trapped in elevators, panic-stricken in darkness and without TV or phones for days. Turns out we had no power for 2 days and only generator owners had a normal life. So this happened Saturday, and schools were closed Monday and today as they are assessing structural damage. Some schools have already been declared out of commission. Our phone lines are screwed up and our drainage lines screwed up, which made the flood on Sunday problematic. So maybe I'll read the second part of that when we talk about hurricanes, because then a hurricane hit. So that, I think, effectively shows that she's just sitting in her car, right? No big deal. It was surreal, as she said. But the people that are inside, when things start falling, that's the danger. So those are the three types of waves. And I wanted to just briefly show you also the first Seismograph, really cool seismograph. Chinese were technological frontrunners for much of human history, and this is a really, really cool seismograph. It's not quantitative, semi-quantitative, I guess. What you have is an urn, and there are dragons at the widest part of the urn, and the dragons are holding balls in their teeth. And if you have the bigger and fancier ones, the dragons will be holding balls with different tensiles, with different strengths, rather. So then at the base of the urn, you have frogs with their mouths open. And in an earthquake, what would happen is the balls would drop out of the dragon's mouths. And the bigger the earthquake, the more balls would drop, because again, they're being held with different strengths. And the cooler thing is it kind of gives you a direction of motion, because if you have that urn here, right, you can imagine if I push this towards you, the balls on the back side would fall out preferentially, and the ones on the front, because you're pushing it forward, kind of stay in the dragon's mouth. So this was a measure, a semi-quantitative measure, if you will, of how bad was the earthquake. These days, we use seismometers, but the evolution from this of how you measure earthquakes progressed to a seismograph. It's really easy to make a seismograph, and I'll show you video footage of this next time, a little animation. For now, you have to deal with to suffer through my terrible hand-drawn diagram. Say we wanted to make, and the children, if you're from California, maybe you've made one of these, the children in schools in California make these regularly. Very simple to make a seismograph. What you would do is use the materials really that we had in the previous visualization. Take an eye hook and put it into the ceiling. Hang a slinky from it. Really, the coils are smaller, but you get the picture. You hang a slinky or a coil from the ceiling, and then that line is a pen. You're done. That's how you make a seismograph. So then how you record it is you guys all have water bottles and things. We can use that. Roll paper along the bottle. And so the pen is touching the paper that's being rolled along your bottle. And what happens is, in an earthquake, because of the principles of physics, the weight, there's a little weight there too. Because of the principles of physics, if this room starts shaking, the coil and the weight will dampen out any movement that the pen will have, but the bottle that we're holding, we're standing on the ground, that we're rolling along, will be moving with the earthquake. So what happens is the pen stays stationary, the water bottle's moving back and forth, and you're pulling it along, so you get to see a recording of the three waves, because they travel at different speeds, right? They all emanate out at the same time, but the P waves travel faster, S waves travel slower, and surface waves travel even slower. So they separate out pretty quickly, and you can see when you're rolling your paper along that you have a movement of the P waves, then the S waves, then the surface waves. Anyone see a fault with this? At some point, the room's also going to move up and down, right? The shear waves go back and forth. The P waves kind of compress and expand. But what happens in a situation like that where you have a pen and a rolling drum doing this, but the room is moving up and down? I told you the weight and the coil dampen out any sort of movement from the pen. The pen will stay absolutely still. So it will happen with the up and down movement. It just skips off, right? There's no recording. Or if it's going up, then it will just leave a darker ink blot. So the horizontal seismograph that we've historically used and that people still make today to show earthquakes, and there's tremendous value in these, you also would make a press Ewing, so a vertical seismograph. Sorry for the bad tiles at the bottom here. These are things that kids also make in schools, in earthquake-prone regions. It operates under the same premise. So here now you have something anchored into the ground, or you're holding it in a rudimentary case. You have a hinge here and an arm. So there's a hinged arm that can go like this. Then you have a coil at the top. The hinged arm and the coil meet at a weight. And then there's the pen. So I drew the rolling drum off the side. So now what happens, again, because of the hinge, the coil, and the weight, that pen will stay stationary even when the room is going up and down. So you would need both of these set up at the front of the room in order to detect whether an earthquake is, or not whether it is, how big it is, and we'll also talk about how you can tell from these seismograms that are generated how far away the earthquake is. So the horizontal one will get the horizontal movement, the press Ewing will get the vertical, and you can kind of integrate the two and figure out what is going on with the earthquake. The seismometers we use now are not physical in nature. You can see old ones. We have them out at the Weston Observatory. You can see physical models. But now we use a light source and a mirror, and we use a detector and electrical recorder. So it's all done with optics and electronics. What's generated in the process of recording the earthquake on a seismograph is a seismogram. So this is the paper we peeled off your water bottle. And again, I'm using just very basic things because it's easy to conceptualize. On the x-axis here, you have the time. So you're pulling the paper along, rolling it up onto your water bottle at a regular speed, at a constant speed. And you see each one of these ticks is 250 seconds. So it's being pulled along. And what happens is, because all the waves happen at first, but if you're close to the earthquake, so someone in the front row would hear them as boom, 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 right? They happen at the same time, one big boom. Then they travel at different speeds. So you hear boom, boom, boom. Someone in the back of the room would experience them as boom, boom, boom. So the greater the distance, the farther away the arrival time between the three waves. So you have the P wave here, you have the S wave, and then there are the Love and Rayleigh waves, those surface waves, the damaging ones. So again, they travel at different speeds. P waves travel at 3.7 miles per second, and S waves only travel at 1.9 miles per second. So it's about 0.6 of a second slower, S versus P waves. So the cool thing is, and we'll do this next time, you can take the time distance in arrival of P and S waves, and you can tell exactly how far away the earthquake was. We'll pick it, we're right at 10:50, so we'll pick it up next time, and we will continue on with pinpointing where an earthquake happened.